So first of all, what are waves? Waves are the transmission of energy from the source to the detector. Just like for oscillations or vibrations, we have a variety of wave parts. We have amplitude, which is the same thing. We have period and frequency, which are also the same thing as in vibrations. Unique to waves, we have wavelength. Wavelength is the length of one wave from where it starts to that position in the next part of the physical wave. We have two ways we can represent waves, which are shown below. We have this kind of wave where if we start here, our wave pattern goes up and then down and then crosses this equilibrium line again. And so therefore what's traced out in blue is one wavelength. And the symbol for wavelength is lambda, and it is generally measured in meters. The other way of representing a wave is the diagram on the left. And if we start right here, we look for where that pattern repeats, and there we have one wavelength for this way of representing a wave. We'll talk about the difference between these two ways of representing waves in a little bit. The last term that we need to be familiar with when talking about waves is pulse. And pulse is a half of a wavelength. And it can either be the beginning part of a wave or the end part of a wave, but it is half of a wavelength. So if we look at our right-hand diagram, there is a pulse, or we could look at the downward portion from here to here. That could be considered a pulse. If we look at our diagram on the other side, we could look at a pulse here, or we could look at a pulse here. It's a little bit harder to see in that type of representation, but you can represent it. When we talk about waves, we have two different types of waves in terms of how they are transmitted. We have mechanical waves and we have electromagnetic waves. We'll start out with their similarities. Mechanical waves and electromagnetic waves all have the same properties. So what that means is they all have amplitudes, they all have wavelengths, they all have frequencies and periods. You can also generate a pulse of an electromagnetic wave or a pulse of a mechanical wave. They are different in how they are transmitted. Mechanical waves need a medium to travel. What is a medium? A medium can be air, water, wood, glass, iron, something, some collection of atoms, some stuff, in order to go from source to detector. The speed of the wave depends on the wave type and the medium. Speed of the waves depends on the density of the medium and its elasticity. Elasticity is the ability of a material to return to its original configuration of atoms or particles. And for mechanical waves, as the density increases and as the elasticity increases, the speed increases. Electromagnetic waves can travel in a vacuum. They can also travel through various types of media, but they can travel in a vacuum. That's kind of their calling card. Because they can travel through a vacuum, put atoms in their way, put a medium in their way, and they slow down. So for electromagnetic waves, as the density of a material increases, they slow down, the speed decreases. So, two big differences again between mechanical waves and electromagnetic waves. Mechanical waves need a medium in order to travel. No medium, no mechanical waves. And as the density and elasticity of the medium increases, the speed increases. Electromagnetic waves don't need a medium. They can travel through a vacuum, but they can also travel through various media. And for them, as the density of the medium increases, their speed decreases. These electromagnetic and mechanical waves can also travel in two different forms. They can travel as transverse waves, or they can travel as longitudinal waves. For transverse waves, the medium moves perpendicularly to the direction of wave travel. Here we have an example of a transverse wave. The wave is moving from left to right, so it's traveling through the medium, and we can see a sine pattern type of travel. The medium is moving up and down, the wave is moving left to right, so the medium is moving perpendicularly to the direction of travel. Here's an example of a longitudinal wave. The wave again is moving from left to right. As we watch it travel, we see that the medium itself is also moving in a direction parallel to the direction of travel. So longitudinal waves, the medium travels or moves in a direction parallel to wave travel. Again, longitudinal waves, the medium moves parallel to the direction of wave travel. Let's take a look at some equations involving the parts of a wave. Wave speed, we talked about the fact that speed depends on what type of wave I have, what type of medium I have. The equation for wave speed you likely have seen perhaps in chemistry, where the velocity or the speed of the wave is equal to its frequency times its wavelength. For the speed of a wave, when I have one wave and it's traveling through a specific medium, its speed will be constant. If I change the medium, what I find is that the speed may change. For wave frequency, for a particular wave, the frequency or the number of waves or cycles per second is constant for a wave, even if it goes from one medium to another. So it doesn't change if the wave crosses a boundary from one medium to another.